back to Calculus 2, Section 2.9, Calculus of the Hyperbolic Functions. We have two topics. We're going to define the hyperbolic functions, look at some basic properties of them, and then go over the inverse of those hyperbolic functions. Let's get started. In the previous video, we went over the exponential functions. Here we're looking at the graph of an exponential function. Base e has a y-intercept of 1. Multiply this function by 1/2, and here is the resulting graph. Reflect this function in the y-axis, and here's the graph. Now let's bring those two together. And the red curve is 1/2 e to the x. The reflection of the red curve produces the green curve, or y equals 1/2 e to the negative x. What we're going to do is we're going to add these two functions to produce a third function. Start at x equals 0. 1/2 plus 1/2 would produce 1. That'll be a point on the new graph. Look in the first quadrant. The red curve has large values, which get larger and larger. The green has positive values, which go down to 0. Moving to the right, you take these red values and add green values, and you'll produce a curve which is always above the red curve, but gets closer and closer. Let's sketch that in. Here we go. So if we take 1/2 e to the x plus 1/2 e to the negative x, we produce this blue curve. Notice the nice symmetry about the y-axis of the blue curve. This blue curve is the graph of our first hyperbolic function. We can read this cosh of x. Cosh of x is the hyperbolic cosine of x. It's defined as a sum of exponentials. Commented earlier, the graph has symmetry with respect to the y-axis. Algebraically expressing that out, if we do cosine of negative x, here's the expression. But notice that we have 1/2 e to the x as well as 1/2 e to the negative x as a sum. In other words, cosh of negative x is cosh of x. Recall that is the idea of an even function. This is the hyperbolic cosine, or cosh, and the evenness of hyperbolic cosine mimics the evenness of the standard trigonometric cosine function. We'll see many other similarities as we go along. Cosh, recall, is the sum of these exponentials. To define the hyperbolic sine, we're going to take the difference of these exponential functions. Let's go ahead and do that. So we have the red curve, 1/2 e to the x, and then the green curve is negative 1/2 e to the negative x. We want to take the sum of these two curves, so 1/2 e to the x minus 1/2 e to the negative x. Consider when x is equal to 0, you'll have 1/2 plus negative 1/2. Our curve is going to go through the origin. As you take positive x's, the red curve has a y value which is much greater than the y value of the green curve. Thus, the sum of these two functions will plot in the first quadrant. Likewise, for negative x's, the green curve has a much stronger negative value than the positive values of the red curve. Thus, our sum function will plot in the third quadrant. Let's go ahead and plot it. So the blue curve, notice, is going through the origin and has nice symmetry with the origin. That the blue curve for positive x's is asymptotic with 1/2 e to the x. The blue curve for negative x's becomes asymptotic with negative 1/2 e to the negative x. Hyperbolic sine, or sinh, is defined in terms of exponential functions. Graphically, we have symmetry with respect to the origin. Algebraically, let's consider sinh of negative x. Plugging into this definition, we'll come up with 1/2 e to the negative x minus 1/2 e to the positive x. Expressing that in terms of the original sinh, we can factor off a -1 and come up with negative sinh of x equaling sinh of negative x. This is the algebraic definition for an odd function. Thus, hyperbolic sine and sine are both odd functions. Very good. So here are the two hyperbolic functions that we have defined. Algebraically, on the right, let's, instead of writing them out as sums and differences, let's write them out as a single expression. Very good. So here's how we will write them out. Let's do some calculus. Thanks to the fact that sinh and cosh are defined in terms of the exponential, taking a derivative is straightforward. E is its own derivative, and by the chain rule, e to the negative x becomes negative e to the negative x. Thus, the derivative of sinh is cosh. And this is in similarity with the derivative of sine being cosine. On the other hand, the derivative of cosh is sinh, and notice that there is no minus sign. And that is in contrast to the derivative of cosine, which produces negative sign. Good. So we have a definition, and then we have a derivative of the function. Thinking about the basic trig functions, which number 6, we can also make definitions for further hyperbolic functions. For example, hyperbolic tangent is the quotient of sinh and cosh. Likewise, the definition for hyperbolic cotangent would be the quotient of cosh and sinh. And hyperbolic secant and hyperbolic cosecant follow the similar definitions. All right, now let's think about the derivatives of these hyperbolic functions. And just like cosh and sinh have derivatives which in a way directly or nearly mimic their regular trigonometric versions, so too will the following four functions. So here are all the derivatives. And it may look like a lot, but if you think of cosh, sinh, and hyperbolic tangent, and then think of their corresponding trigonometric versions, then you can write all of those down and leave off any minuses. to come up with the formulas. And the remaining 3, if you recall, the derivatives for the corresponding trigonometric functions, then you know how to differentiate these hyperbolic trig functions and always include a minus sign. So cosh, sinh, and hyperbolic tangent, no minus signs in the derivatives, and then the remaining 3 always have a minus sign. Very good. Let's do an example. So we just went over the derivative for hyperbolic tangent. Let's look at the derivative of hyperbolic tangent evaluated at x squared. So a nice composition. Given that hyperbolic tangent has derivative, the square of hyperbolic secant, we evaluate that derivative function at the original input and then differentiate the original input. X squared differentiates to 2x. Beautiful. All right. So we made the definitions for hyperbolic trig functions. We looked at the derivatives and saw some similarities. If we think back to a circle centered at the origin, radius 1, we can write down x squared plus y squared equals 1. This is directly related to the Pythagorean theorem and leads nicely into the Pythagorean identity. Cosine squared of theta plus sine squared of theta is equal to 1. We want to come up with a similar identity for hyperbolic trig functions. Let's take a look. So consider cosh, defined in terms of exponentials, sinh, defined in terms of exponentials. One is a sum, one is a difference. The Pythagorean identity is cosine squared. Let's likewise consider the square of cosh and sinh. Okay, so we take the definition in terms of exponentials and square either side. Good. All right, so the real work is going to be in squaring the numerator. Let's separate that out. Bring out the 2 quantity squared in the bottom, and then consider this binomial squared. So we have a binomial multiplying with itself. E to the x is going to meet up with e to the x. E to the negative x will meet up with e to the negative x. And then the mixed term is going to be e to the x times e to the negative x, but that's the reciprocal of e to the x. So something times its reciprocal, you get back 1. How many times can that happen? Twice. Very good. So let's swap out that binomial squared with its expanded version. And given that sinh is nearly identical to cosh, except for instead of being a sum, it's a difference. In multiplying out, the only difference will be instead of a plus 2 mixed term, we get a negative 2. Okay. So if these were the regular trig functions, cosine squared plus sine squared would produce 1. Think of that right-hand side 1. And then look at these squared values. And we have e to the x times itself, appearing both in cosh squared and sinh squared. We can easily remove them if we take the difference of these two terms. So all the exponential terms will cancel out. And then we're going to take cosh squared and subtract away sinh squared. So on the right-hand side, that's going to be 2 minus negative 2, which produces 4. Then considering the coefficient 1/4 out in front, that's 4 over 4, or 1. This is the identity for, or an identity. There are many, many identities, but this is a salient identity for hyperbolic trig functions. Compare and contrast that with the Pythagorean identity. Whereas the Pythagorean identity is a sum, you don't need to specify the sine squared or cosine squared first. Either is fine. But in the hyperbolic version, as it is a difference, you need to be careful that it's the cosh, which is first squared, minus sinh squared. Excellent. All right. So here's that identity that we just went over. And one place where it is employed is in verifying the derivative for hyperbolic tangent. Verify this derivative by writing out hyperbolic tangent as sinh over cosh, and then take a derivative. Excellent. Here is another identity. This one mimics the sum identity for sine. And to verify this, go back and use the exponential definition for sinh. And perhaps it will be helpful to expand on both sides. Use the definition on both sides and show that you can produce the same expression on either side. Beautiful. So that is an elementary overview of hyperbolic functions, which we started with exponentials to produce hyperbolic functions. Exponentials, you will call, are one-to-one functions. As hyperbolics are defined in terms of one-to-one exponentials, it stands to reason that the hyperbolic functions have inverses. This is the graph of sinh. Sinh is one-to-one. Well, if it's one-to-one, we can invert it. We can graphically produce a function. How about algebraically? What is the inverse of hyperbolic sine? Let's investigate. So algebraically, put a placeholder down. Y is the inverse of hyperbolic sine. All right, well, how do we proceed forward? Well, we know that this guy, inverse hyperbolic sine, is the inverse of hyperbolic sine. So reterm things in terms of hyperbolic sine by taking sinh of either side. Good. All right, what's next? Well, how did we come upon hyperbolic sine? We made a definition. So recall back the definition for hyperbolic sine and plug in. So I've plugged in and also multiplied by 2. Okay, so what is it that we're doing? We're trying to investigate, trying to get a better grasp on the inverse hyperbolic sine, which in shorthand is just y. So we would like further information on y. All right, well, y is appearing as the power to e, but also as e to the negative y. All right, that looks a little bit troublesome. What can we do? Okay, so you spend lots and lots of time studying algebra. Everybody does. because it is applicable in many situations. It's a wonderful tool. Let's see. So we're going to multiply by e to the y. So e to the y times e to the y. E to the y times e to the negative y goes to 1. And then bringing the 2x to the left introduces a minus, and 2x e to the y. Okay, we have a right-hand side of 0. And if you think back to algebra, we have parentheses around this term, we have 2x times that term, and then we have a constant. Notice that this is quadratic in e to the y. Aha! So now that means that we can use the quadratic formula. Basic algebra. Okay. Plug into the quadratic formula, and our unknown e to the y can be expressed out as 2x, so negative b, plus or minus the radical of 2x squared minus 4ac, just 4, all over 2a. Nice. So this right-hand side, let's simplify it, is purely algebraic in terms of x. That is very, very nice. But on the left-hand side, we have e to the y. Before getting rid of the base e, let's make an observation. Something very, very nice about the exponential is that it is always a positive value. We're trying to investigate this guy y, which is supposed to be a function. So having e to the y be this plus or minus is a little bit concerning. Oh, but e to the y is always positive. If, look at the radical term, if we were to take the square of x squared, ignore the plus 1, we would have exactly x. And then x minus x would be 0. So x squared plus 1 is bigger than x squared. Therefore, this radical will be bigger than x. Well, small minus big is negative, so we better throw away the minus. Looking much better. Good. Now we can remove the base e, as the exponential is the inverse to the natural log. Apply the natural log to both sides, and we will have isolated y. Right-hand side will be the natural log of this expression. This expression is going to be positive, provided that x is positive. And then recall that y is the inverse of hyperbolic sine, and hyperbolic sine was defined in terms of exponentials. And we're finding that inverse hyperbolic sine is defined in terms of the natural log. Very good. All right, so you can verify that if you were to differentiate this right-hand side, after some algebra, you could simplify and produce this right-hand side. We can accomplish this differentiation formula in an alternative way. Go back to our definition of y being inverse hyperbolic sine. Restate that in terms of sinh, and then differentiate. Sinh goes to cosh. This is a different derivative with respect to x. So by the chain rule, pick up dy dx. Right-hand side, x differentiates to 1. We're trying to figure out what is the derivative of inverse hyperbolic sine, so solve for dy dx. Get 1 over cosh of y. Okay. Now, we want to express out the derivative of inverse hyperbolic sine as a function of x. Currently, we have it as a function of the original function. Kind of strange. So let's play around. Well, we can go back to our nice identity. Cosh squared of input minus sinh squared of that same input will produce 1. We have here in the denominator cosh of y. Let's take this identity and solve for cosh of y. So move the sinh squared to the other side. We want cosh of y, so let's apply a radical to both sides. So now we have this expression, but this expression is still in terms of the original function. Oh, but wait. If we take y and pass it into sinh, that'll be exactly x. Thus, cosh of y can be written out as radical x squared plus 1. And that establishes that the derivative of inverse hyperbolic sine is 1 over the square root of x squared plus 1. Very nice. Your turn. Establish that the derivative of inverse hyperbolic cosine takes a very similar form, but instead of the radicand being a sum, the radicand is a difference, x squared minus 1. Beautiful. Now, an application of hyperbolic trig functions is that hanging cables follow the graph of a hyperbolic trig function. Call it a catenary. So suppose that you have power lines hanging following this curve for this input, negative 15 to 15, and then determine the arc length of this power line. Very nice. That finishes up this section. Thank you so much for watching. See you on the next one.